नमस्ते बच्चों, हमेशा खुश रहो. Myself, JVn Dr Monika Trivedi. Today I am going to teach you Carnot cycle and its efficiency and Carnot theorem. This topic belongs to paper Thermodynamics, Equilibrium and Solution of B.Sc, B.Ed, PCM, ZBC and B.Sc, PCM, ZBC 4th semester. So, before knowing the Carnot cycle, we have to know about what is a heat engine and what is the efficiency of a heat engine. So, the flow of the heat from the hotter body to the colder body is a spontaneous process. Okay, the heat that flows out the spontaneously can be used to do work with the help of the suitable device. Okay, a mechanism which can be do work by using the heat that flows out the spontaneously from a high temperature sources to a low temperature sink is called a heat engine. Okay, and what is the efficiency of heat engine? The ratio of work obtained in a cyclic process, which is a W, to the heat taken from the high temperature is Q. Is referred as a efficiency of the heat of the engine. No heat engine, no matter how well constructed, can convert all the heat from the high temperature into a work. Such an engine would be has a 100% efficiency. Okay, so this is a heat engine, and what is the efficiency of heat engine? So now we discuss about the Carnot cycle. What is a Carnot cycle? Generally, in 1824, Carnot proposed the theoretical generalization of heat engine that show that the efficiency of the heat engine depends upon the temperature between which is operated. Okay, so Carnot's imagine engine which can perform between the temperature T1 and T2, and this he studied this system which is restored the original state of the engine. Okay, so generally this cycle has a four process including the isothermal reversible expansion, second is adiabatic reversible expansion, third is isothermal reversible expansion, and fourth is adiabatic reversible compression. Okay, two processes are compression and two processes are for expansion of the gas. Okay, so this Carnot's cycle system depends upon the expansion of gas and compression of gas. Here you can see the diagram of a Carnot cycle. The curve A and B represented the isothermal, curve B and C is represented for adiabatic process, curve C and D represented isothermal process, and curve D and A represented adiabatic process. Okay, so for the first process, okay, for the isothermal reversible expansion, as we know T2 is the temperature, P1 and V1 volume and pressure. Okay, so let T2, P1 and V1 be the temperature, pressure and volume represented respectively for the gas which encloses in a cylinder. Okay, this the cylinder is placed in the heat reservoir at the high temperature, like T2 is a temperature. Now the gas is allowed to expand isothermally and reversibly so that the volume increases from V1 to V1. Okay, so as we shown in curve A B. Okay, the first is A B curve and the isothermal temperature T2. So in AB represented the path of the process in a diagram. Work done, what is the work done in that time? So since the process is operation 1, so the isothermal del E is equals to 0, work is a 0, and if Q2B the heat absorbed by the system and the V1 the work done by the system, so according to first law of thermodynamics, the first law of thermodynamics is del E is equals to Q minus W. Okay, if the heat is Q2 and the work is W1 for this first operation, so what we have Q2 is equals to W1 and W1 is equals to RT2 ln V2 by V1. Therefore, Q2 is equals to RT2 ln V2 by V1. See, okay, this is equation 1. Second operation is adiabatic reversible expansion. Okay, the gas at B point at the temperature T2 and has a volume V2 under the new pressure P2. There is a pressure changes. Okay, the gas is now allowed to expand reversibly from volume V2 to V3 when the temperature drops from T2 to T3. The graph of B.Sc. Okay, so the work done is because this system is a adiabatic. So for the adiabatic system, Q is equals to 0. So the work done, which is V2, according to first law of thermodynamics, is equals to del E is equals to minus W2, because the heat is 0 for adiabatic process. So what we get, W2 is equals to minus del E. Okay, so del E is equals to CV T minus T2 T1 minus T2. So here we can put the value of del E. So we get W2 is equals to CV T2 minus T1. This is equation 2. Now the third operation, which is isothermal reversible compression. Okay, now the cylinder is placed on a constant with the heat reversible at the lower temperature T1. The volume of the gas is then compressed isothermally and reversibly from V3 to V4. Okay, represented in graph CD. The work done during the compression of the gas produces the heat which is transferred to the low temperature reservoir. Since the process takes place isothermally, the del E is equals to 0. Del E, internal energy change, is equals to 0. So if the Q1 is the heat give to the reservoir, and the W3 the work done on the gas using the proper sign for the QW, what we get minus Q1, because there is a compression. Okay, depression. So we use here a minus term. So minus Q1 is equals to minus W, which is equals to RT1, because temperature is T1 here. So we put here RT1 ln and volume is V4 by V3. This is equation 3. For the fourth operation, and the fourth operation is adiabatic reversible compression. The gas with the volume V4 and the temperature T1 at the point D compressed adiabatically until it reaches the original state. That is, the volume of the system become V1 and the temperature become T2. Okay, so the work done at that step on the system, and therefore the negative sign is we get. Okay, so if the work is W4, so what we get minus W4 is equals to minus CV temperature T2 minus T1. This is equation 4. If we want to calculate the overall work done on the system for by the this Carnot cycle, we have to calculate the net work done by this all equation. We have to put the all equation together like 1, 2, 3, 4, and we can calculate the work done by the overall system. So if we calculate the overall work done by the system, we have to W is equals to W1 plus W2 plus we have to add all the works from the 4 operations. So what we get, W is equals to W1 plus W2 plus, because W3 is in a form of minus, so we put here minus W3 plus W4 is in a form of minus. Okay, because in both minus processes, minus sign, the work done on the system. Okay, so what we get finally, we have to put the values of W1, W2, W3 and W4. Okay, so here we can put the value of W1. We finally get the R2 ln V2 by V1 plus R T1 ln V4 by V3. Okay, So the net heat absorbed in a one cycle, if a q is the net heat absorbed in a whole cycle, so the q is equals to q2 minus q1, change in heat. Okay, where q2 is heat absorbed by the system in operation 1, and q1 is the heat transferred from the sink reservoir from the reservoir. So from equation 1 and 3, previously where we learned about equation 1 and 3, q is equals to q2 minus q1, which is equals to r2 rt2 ln v2 by v1 plus rt1 ln v4 by v3. Okay, and here we can put q is equals to r2 rt2 ln v2 by v1 minus, because this sign converted into minus, and here we can change the value of volume, like minus RT1 ln V3 by V4. This is equation 5. So according to the expression, the adiabatic processes, for the adiabatic processes, T2 by T1 is equals to V3 by V2 gamma minus 1. Okay, and for the adiabatic compression, T1 by T2 is equals to V1 by V2 gamma minus 1. If we equate both the equation, like V3 by V2 is equals to V4 by V1, what we get, or we can put the equation like V3 by V4 is equals to V2 by V1. Therefore, by substituting the value of V3 by V4 in equation 5, okay, the value of net heat may be calculate. Okay, so if we put the value V3 by V4, and we put the value of V3 by V4 in equation 5, which is V2 by V1. So if we put the value of V3 by V4 in that equation, what we get, Q is equals to RT2 ln V2 by V1 minus RT1 ln V2 by V1. Okay, and finally we get Q is equals to R T2 minus T1, the common, and ln V2 by V1. So if we calculate the thermodynamic efficiency of that engine, since the total work done in the cycle is equal to the net heat absorbed from the equation 6. So here Q is equals to W. So we can write here W is equals to R T2 minus T1 ln V2 by V1. The absorbed heat Q2 at the high temperature T2 is given by the equation 1. So Q2 is equals to R T ln V2 by V1. Hence, if we divide equation 7 by equation 8, what we get, W divided by Q2, and RT2 minus T1 ln V2 by V1 is divided by RT2 ln V2 by V1, and where we get T2 minus T1 by T2. So the efficiency of engine, like W by Q2 is equals to T2 minus T1 T2. So the factor W by Q2 is called thermodynamical efficiency. It is denoted by neta, and gives the fraction of the heat taken from the high temperature reservoir, which is possible to convert into work by the heat engine. Therefore, the efficiency of Carnot engine, the most ideal of the engine, is limited by the operation temperature of the engine. The larger the temperature difference, like T2 minus T1 between the higher and the lower temperature reversal, the more heat converted to the work by the heat engine. For a given temperature, the higher temperature reservoir, the lower the temperature of the sink, the greater the efficiency of the machine. Similarly, for the given temperature of the sink, the efficiency will be increased by using a high temperature of the source reservoir. Okay, what is a Carnot theorem? Carnot theorem is the efficiency of an engine. So here you can see W by Q2, which is the efficiency of engine, is equal to T2 minus T1 by T2. The result of a Carnot engine, the Carnot, this absorption of heat is known as a Carnot theorem. So every perfect engine working reversibly between the same temperature limits has the same efficiency wherever it is working on a substance. So this is all about Carnot engine and Carnot isotherm. Thank you very much. This session powered by Digital Version 2.0 Jyoti Vidyapeeth Women's University. Hope you satisfied with my session, and if you have any query, comment me. Thank you.